In this video, we are going to complement the theory a little bit and explain some properties of the big O and little o notation. This is a notation that's widely used in mathematics, but we are going to explain here only the particular case concerning Laurent series at Z0. So what is the setting? We have a function f, which is holomorphic with an isolated singularity at Z0. Holomorphic and Z0 isolated singularity. Then we know that f has a Laurent series, sum for n going to minus infinity to plus infinity of a times z minus z0 to the n. And now what we want to say is we want to give a name to a function f such that many of these coefficients are zero, the coefficients an, and more precisely, the coefficients with index smaller than some threshold. So we say that f is a big O of z minus z0 to the k for some k integer as z tends to z0 if the coefficients an is equal to 0 for all n smaller than k. So basically what we are saying is that the Laurent expansion of f contains terms only of order bigger or equal than k. So this means Laurent series contains only terms of order k or higher. So this means that if you want to start writing the Laurent series, then you will start with a k times z minus z0 to the k plus ak plus 1 times z minus z0 to the k plus 1, and so on. Okay, so this k here will be the smallest k. So before all the others are an will be 0 when n is smaller than k. So this is the notation for the big O, and then we also write f of z is equal to a big O of z minus z0 to the k. So this is also the notation we are going to use. And there is also a similar notion of the small o, and this is really similar, and in some sense the two notions are equivalent. And in this notion, we are requiring that all the coefficients are 0 for n smaller or equal than k. So this means the Laurent series contains terms only of order k plus 1 or higher. So let me give this definition. We say that f is a small o of z minus z0 to the k as z tends to z0 if an is equal to 0 for all n smaller or equal than k. So this means Laurent series contains terms of order k plus 1 or higher. So we write in this case f of z is a k plus 1 z minus z0 to the k plus 1 plus a k plus 2 k plus 2 and so on. And in this case we write f of z equal to small o of z minus z0 to the k. So you see the two notations are really equivalent. So observation that fz is a big O of z minus z0 to the k is k plus 1 if and only if f of z is a small o of z minus z0 to the k. Okay, so sometimes it's just more useful to think in terms of big O's, sometimes in terms of small O's, but the two notations are really used for the same purpose. So let's maybe see an example. So in this example, we can consider, for example, e to the z. And I know that this has a series expansion at z0 equal to 0, given like this. So here I have terms of order bigger than 2. So I just simply can rewrite this as 1 plus z squared over 2. And here there will be terms of order bigger than 2. So this will be an O of z squared, z cube, or which is equivalent O of z squared. Okay, so this simply means that the exponential has 1 plus z squared over 2 as the first three terms, the power series expansion, and all the others have order bigger than 2, or which is equivalent bigger or equal than 3. And there is also one notation which is commonly used. Maybe I can recall it here. Is that instead of writing O of z minus z0 to the power 0, so when k is equal to 0, you can just write O of 1. So this is the notation which is used, and same for small o. Okay, very good. So these definitions are then useful when we want to do operations with functions. So let me recall some rules for computation. So the first thing is that if I have f, which is big O of z minus z0 to the k, then this f will be also a big O of z minus z0 to the h for all h smaller or equal than k. Also, if I know that all the terms coefficient with index smaller than k are 0, well, then it means that also all the coefficients with index smaller than h are 0 if h is smaller or equal than k. So this is what I am saying here. Then second rule is when we want to sum or multiply two functions. So if we have f of z, which is O of zk, and g of z, which is O of zh. So here I'm taking z0 equal to 0 in order to simplify a bit the notation. Then what happens? So then f of z plus g of z will be of order z and the minimum between h and k. Okay, so this is also clear why this is true, because f of z plus g of z will have expansion given by the sum of the coefficients, so an plus bn z to the n. So if I know now that an is equal to 0 and bn is equal to 0 for all n smaller than h, and for all n, sorry, this is for bn. So let me do the two cases separately. So if we know that this is 0 for all smaller k, and bn is equal to 0 for all n smaller than h, well, then the sum will also be 0 for all n which is both smaller than k and smaller than h. Also, but this means n must be smaller than the minimum between h and k. Okay, and another useful rule is with the product. So when we have instead the product of two functions, then now this is a big O of z, and I get here k plus h. Okay, this is also intuitive why this is true, because if f of z is equal to a k z to the k plus a k plus 1 zk plus 1 and so on, then this means that this is z to the k times a function f1 of z, and this function here is holomorphic. And then the same for g of z. This will be z to the h times a function f g1 of z, which is also holomorphic. And so in the end, we find that f of z times g of z This is Z to the K plus H times F1 times G1. Okay, so this F1 times G1 has some power series expansion times some B0 plus B1 Z and so on. So you see that also here, the first coefficient appearing is K plus H. Okay, so this is also the rule for the product, the rule for the sum. And also we observed here in the first property that if something is a big O of some K, then it's also a big O of all the H smaller or equal than K. And very similar rules hold also for the small O notation. So let me now see a couple of examples where we can use this notation to compute the first orders of some power series. So example, suppose you have f of z, which is 1 plus z over 3 minus z squared over 5 plus some terms which are of higher order and some g, which is given by 2 plus z squared plus some term of higher order. Then what we want to find our series of f plus g and f times g at z0 equal to 0 up to order 2. So this is what we want to do. And here you see for f of z plus g of z, in this case, we have 1 plus z over 3 minus z squared over 5 plus O of z squared plus 2 plus z squared plus O of z squared. So now the terms here, we have two terms of order bigger than 2. And when we sum them up by the rule 2 of the sum, they remain of order bigger than 2. So we can then put these two terms aside, because we know that these terms here will remain, the sum of these two terms will remain of order bigger than 2. So we have of order 1, we have 1 plus 2. Sorry, of order 0, we have 1 plus 2. Then of order 1, there is only z over 3. And of order 2, there is z squared and 1/5 z squared. And then all the other terms are of order bigger than 2. So see, every time, if I write only once O of z squared, because if I have two terms here of order bigger than z squared, they can be summed up together and they both give order anyway higher than 2. So here we find 3 plus z over 3 plus 4/5 z squared plus terms of order bigger than 2. Okay, so this is the result for the sum. Let me now do the product. So what is f of z times g of z? Then f was 1 plus z over 3 minus z squared over 5 plus O of z squared. We multiply this by 2 plus z squared plus O of Z squared. Okay, so now we have this product. Let's use simply the distributive law. So we have 1 times 2 is 2. 1 times Z squared is Z squared. 1 times OZ squared is OZ squared. And then we have Z over 3 times 2 plus Z over 3 times Z squared plus Z over 3 times O of Z squared. Then what's left is minus Z squared over 5 times 2 minus Z over 4 divided by 5 minus Z squared over 5 times O of Z to the 5, Z to the 2. And then there is also some other terms, but these are O of Z to the 5 times 2 plus Z squared plus O to the Z to the 2. Sorry, not Z to the 5, but Z to the 2. Yeah. Okay, so now we can just see what terms of order smaller than 2, smaller or equal than 2. So what are the terms of order smaller or equal than 2? Okay, so 2. Z squared, then I have a term of order bigger than 2, then Z times 2 over 3. Then here I see I have Z times Z squared, so this is a term of order Z cube. So this is not of order smaller or equal than 2. So so this one here is Z cube divided by 3. And so this is small o of Z squared. Then here we get a term which is of order bigger than Z cube, because we have Z times orders of which are bigger than Z squared. Then we get now once again a term of order 2. So these is also interesting for us. And then we have a terms of order 4, which is shortly some O of Z squared. And then here also we have O of Z4. And then here also O of Z2 times this 2 plus Z squared plus O of Z squared. This is also O of Z2. Okay, so now we have the only contribution which are of order smaller or equal than 2 are the one highlighted in yellow. So we find 2. This is the only one of order 0. Then the one of order 1 is just 2/3 times Z. And then of order 2, we have 2 of them, Z squared, and then minus 2/5. And all the others are of order bigger than 2. So in the end, we find that this is the power series expansion of F times G up to order 2. Okay, so this is one exercise. So I want to finish with another exercise which is a bit more involved, so we can see then all the possibilities that we have. So let's consider then the following function: f of z equal to 1 divided by 1 minus sinus of z. And what we want to do, we want to find power series expansion of f, at Z0 equal to 0 up to order 4. So you see we have 1 over 1 minus sinus of Z. So the idea is to use the formula for the geometric series. So what we do here, we observe that sinus of Z is equal to Z minus Z cubed over 6 plus terms which are of order bigger than actually 4. The next term here would be Z to the 5 over 120. So in particular, now you see this means that sinus of Z is Z plus terms of order bigger than Z squared, or you can also write this. So this also implies that sinus of Z is as order Z or bigger. Okay, so now is useful information, because now sinus of Z, sinus of 0 is equal to 0. This means we can use the formula for the geometric series. For to find the expansion. So we see here f of Z becomes 1. So this is 1 over 1 minus sinus of Z. And using the formula for the geometric series, this is 1 plus sinus of Z plus sinus of Z squared plus sinus of Z cube, and so on. And now you see here, we want to get a power series expansion up to order 4. So the question is, which of these terms, sin Z squared, sin Z cubed, sin Z to the 4th, give us terms of order up to 4. So since sinus of Z is of order Z, then starting from the 5th power, this will all have order bigger than 4, terms of order bigger than 4. Because sinus of Z is of order Z implies that sinus of Z to the K is of order Z to the K. And here we are using the rule, this rule here for the product. So applying this rule, then we find that sinus of Z to the K is of order O Z to the K. And this is also O of Z to the 4 if K is bigger or equal than 5. Okay, so we see that we need only to consider power of sinus to the sinus of Z up to order 4. So all these terms here then are O of Z. So we don't need them if we want to compute our series expansion up to order 4. And now we have these terms, 1 plus sinus of Z, sinus Z squared, sin Z to the 4th. We want to find here terms of order up to 4 for this function here. So for sinus of z, we already done this. You see sinus of z is z divided by 6 plus terms of order bigger than 4. So let me rewrite this maybe here. Sinus of z, it's already done, is z minus z cubed over 6 plus terms of higher order. Now what happens to sinus of z squared? So in this case, we have to multiply sinus of z with itself. Okay, and here, as a rule, you see, you can always get rid of O z to the 4 and bring it outside. So this is z minus, also maybe I can write this directly as squared. And now here, this is clear because every time I multiply a term of order z to the 4 with z or z cubed divided by 6, then I get something of bigger order. So if you want, you can check this passage here maybe more carefully, but in the end, what you see is exactly this identity. And then now I can do the squared. This is z squared, then plus z to the 6 divided 6 squared minus 1/3 z to the 4th. Okay, so you see here we get z to the 6 is also of order bigger than 4. So in the end, we find z squared minus 1/3 z to the 4th plus O of z to the 4th. Okay, so this was the square of sinus of z. Now let's do the cube. And for this, we can already use the formula for z squared. And now put here z minus okay, so once again, this is z squared minus 1/3 z to the 4th times z minus z cubed plus higher order terms. And now if you do this computation, you see that you get z squared times z, or maybe, right, z cubed, then z squared times z to the 3rd is of order higher than 4. I can ignore it. And all the other terms are of order higher than 4 because then I have z to the 4 times z and z to the 4 times z to the 3. So this is the only term of order smaller than or equal to 4. And then for the same reason now, if I want to do sinus of z to the 4th, then I get z to the 3 and then here you see I can just substitute instead of sinus of z, z plus O what was it? Sorry, z again minus z cubed 6 plus O z to the 4th. And here I get z to the 4th. And then it's easy to see that all the other terms are of order bigger than 4. Okay, so now we are done with this long computation. So let me highlight all the terms of order smaller than or equal to 4. Here we get z to the 4, here z to the 3. Here these two terms. And for sinus of z, this was these two terms here. So now we can substitute back and find the expansion for f of z. So f of z, then this was 1 plus sinus of z, and this gives me these two terms. Then sinus of z squared, and this gives me these two terms. Then sinus of z cube, and this gives me only z cube. And then sinus of z to the 4th is z4. Okay, so then we have it. We can just maybe rewrite a bit better. So 1 is the only term of order 0. Then terms of order 1, there is only z. Terms of order 2, there is only z squared. Then we have a couple of terms of order z cube. Summing them up will give me 5/6 z to the cube. And then we also have a couple of terms of order z to the 4, which gives me this. Okay, and then finally we got the expansion that we wanted up to order 4. So you see it's a bit of computation, but in the end, it's all elementary. Okay, thank you for watching.